Okay, this is section 6.2. This is representations of functions. And we have something called a function rule. So a function rule is an equation that describes the relationship between the inputs, which is the independent variables, and the outputs, which is the dependent variables. So remember, the dependent variable depends on the independent variable. Okay, so here's our little visual. If your input, you're inputting -2 into the function rule. We call this the function machine. And the function is y equals 3x. So when you input -2 for x, it outputs a -6. So the first example is it wants you to write function rules. So it wants you to write a function rule for the output is 5 less than the input. Remember, output is y, input is x. Okay, and then we have some other keywords. We have is, which means equals, and then 5 less than. We know it's going to have something to do with subtraction. Okay, so my function rule would be y equals 5 less than the input. Normally you can read these from right to left and use that order, but this word less than changes the order of these values. So it's really y equals x minus 5. So the output, y, is 5 less than the input. Same thing for b. The output, which is y, is equals the square, which is like the little exponent of the input. So this would be y equals the square of the input. Example 2, what is the value of y equals 2x plus 5 when x is equal to 3? So this really is as simple as it looks. So you are going to plug x equals 3 in for x. Then you have y equals 2 times 3 plus 5. So this is y equals 6 plus 5, and y is equal to 11. All right, these are on your own. So I encourage you to pause this video, try these 3 problems on your own, and then resume the video when you're finished to check your answers. The output is 1/4 of the input. Okay, so I have the output, which is y, is 1/4 of the input of, also means multiplication, is equals 1/4 of the input. All right, for number 2, all of these you evaluate when x is equal to 5. So you're going to plug in x is 5 for this x, and also for the x in number 4. So this is y equals 4x minus 1. So y equals 4 times 5 minus 1, which is 20 minus 1, which is 19. Number 3, I have y equals 10x, which is the same thing as y equals 10 times 5. Y is equal to 50. And the last one, y is equal to 7 minus 3x. So y is equal to 7 minus 3 times 3. Times 5. And we have 7 minus 15, and y is equal to -8. Yes, it really is that simple. Our next key idea is functions as tables and graphs. So a function can be represented by an input-output table and also by a graph. The table and graph below represent the function y equals x plus 2. Now you guys are probably thinking, why are we going backwards? Why are we going backwards and having to make tables in order to graph equations? And it's because they're not always going to just be a slope and a y-intercept. Okay, I'm going to start to give you things like x cubed and 1/2 x squared plus 2 plus 0, something like that. And you're not going to be able to graph this by just graphing this 0 and graphing the slope. Okay, so you're going to have to go back and remember how to do input-output tables. Okay. So example 1, once again, you're going to think this is kind of silly because this is just one that you could easily graph using a slope and a y-intercept, but we're going to go back and practice making our function tables. So input-output table, I have my input, I'm going to have my equation, and my output. Okay, so it says use the input of -1, 0, 1, and 2. So my equation is -2x plus 1. So this would be -2 times -1, which is my input. So I have -2 times -1 plus 1, So positive 2 plus 1 is 3. This one I have negative 2 times 0 plus 1, which is 1. This one is negative 2 times 1 plus 1, which is negative 1. And lastly, negative 2 times 2 plus 1 is negative 3. Okay, so my ordered pairs are my input, comma, output. So I have input, output, input, output, input, output, and the last one is 2, negative 3. Okay, so I need to take these ordered pairs and I need to plot them on my graph. So I have negative 1, 3. I have 0, 1. I have 1, negative 1, and 2, negative 3. Once you plot the points, just make a line connecting through those points, and you're finished. All right, on your own, graph these functions. You must make a table. Okay, I know you can plot these graphs much easier, but I need you to practice making a table. I'm going to pause this because it takes me too long to write, and I don't want you to sit here and have to watch me make a table. So do these on your own. When you have finished 5, 6, and 7, hit play and see if you have the same answers as I do. Alright, hopefully you tried these on your own first. Notice I just used a negative value, a 0 value, and a positive value for all 3 of my input-output tables. And yes, they can be this simple. You don't have to do the whole equation part as long as you can easily do it in your head. Some equations you'll have to, others are much easier. Alright, example 4 is our real-life applications. The number of pounds of carbon dioxide produced by a car is 20 times the number of gallons G of gasoline used by the car. Write and graph a function that describes the relationship between P and G. So our variables instead of X and Y are P and G. So I'm going to have P is equal to my output, and G is equal to my input, because the number of gallons I put in depends on how much carbon dioxide is produced. So this is my dependent variable, and this is my independent variable. Okay, so my function. So the amount of carbon dioxide that is produced is P equals 20 times G. So every gallon I use, 20 pounds of carbon dioxide is produced. So I need to make an input-output table for the function. Now I'm going to ask you, normally I would make you do negative values, a 0 value, and a positive value. But for this case, a positive value, or excuse me, a negative value doesn't make any sense. Okay, this is all going to be positive values on this graph. So what I would just do, I'd just do 0, 2, and 4. Okay, so when 0 gallons of gas are used, 0 pounds of carbon dioxide is produced. When 2 gallons are used, I do 2 times 20, which is 40. And when 4 gallons are used, I do 4 times 20, which is 80. Okay? And remember, when you graph this and you're not counting by ones, you must label and tell me what you're doing. Okay? It can be very, that's not what I wanted to do. It can be very simple. And you can spread it out as much as you like, but you have to tell the reader of the graph what you're doing so they're not looking at the graph and wondering what the heck you're doing. Okay? So I would just go up and count by 20s. So I would do 20, 40, 60, and 80. And then, so 0, 0 is here. 2, I go up to 40. And 4, I go up to 80. So you're really only using the first quadrant of this graph, because all of these values would have a negative value. And lastly, here's just a summary of how to represent a function. You can represent it in an input-output table. You can represent it in words. You can represent it in an equation, also a mapping diagram, and also a graph. You need to be familiar with all 5 methods. Okay? We will be using these throughout the chapter, so you need to be familiar with the words, the equations, the input-output, mapping diagram, and also the graph. That's it. See you later.